So this time I'm going to start a little bit high level and then kind of work my way down. Let's ask ourselves, why are we here? So maybe because your boss sent you here, maybe because you want to hang out with your friends. Those are all very valid reasons. One reason that Phil mentioned yesterday in his opening speech is that maybe we're here because you all want to write better C++. But in order to figure out how to do that, we need to figure out what does it mean to write better C++. In fact, what is good C++? Or what is a good program? And I think we all have ideas about that. That's why we're software engineers. There's a lot of things that make a good C++ program. One thing that immediately comes to mind is, a good C++ program is efficient. This is probably what at least half of talks about C++ tend to be about. This is like the unique selling point of C++. It's performant, right? That's part of efficiency. There's usually lots of talks and books being written about lots of other properties that good code and good programs have, like they're maintainable, readable, extensible, portable, reusable, scalable, all of these things. C++ can be good for all of those things. One that is sometimes overlooked is, of course, cost-effective. A good program isn't really a good program if you don't have the budget to develop it and then ship it. And then there's two here that have received particularly high attention in the last couple of years in the C++ community, which are safety and security. So I want to talk about those two. But before I do that, there's one really important one missing here. Can somebody tell me which one that is? Yes. Yes, of course, correct. And that is, of course, the most important one, because if your program isn't correct, then it doesn't really matter, what else it does, because it doesn't do the thing that it's supposed to do. So what is a correct program? That is a question that we need to ask ourselves. And so if you look into kind of computer science and literature, there's a bunch of definitions there. There is this notion of functionally correct. A program or an algorithm or a function set is functionally correct for any input. The output matches what the specification says the output should be. That is hopefully something that is very intuitive. But then it gets a little bit more complicated. So there is like this distinction between total correctness and partial correctness. So total correctness is when an algorithm actually does return an output, and then when it does, that output is correct. So you see where this is going, right? So if you want to prove that property, you run into the halting problem. That's in general undecidable. So there is this kind of other notion, which is partially correct. So we can't prove that a program returns a value, but if it does, then that is correct and satisfies the specification. So that is where you can prove things. There's mathematical formalisms that you can throw at this. The whole logic is one particular framework of thinking that you can apply here. So there's lots of tools and approaches that build on that to prove partial correctness. However, I'm not going to go into this today. This kind of mathematical approach is very valuable, very interesting, also very complex. And I personally found that it doesn't scale particularly well for real-world code and real-world problems, like real big code bases that actually do stuff in the real world. So there are places where you can apply this, but it's not practical, at least for some cases. So we need something that's a little bit more empirical, a little bit more practical. And the problem here is that the real world is messy, right? So when we say for any input, the output satisfies specification, what is the specification? Where and how is it specified? What is the input and output? Is it the parameters I pass into a function, return value? Is it what happens when I have stat_c in, stat_c out? Maybe my program produces sound or talks to the network or does something else. Is that also input and output? Is that something else? What about side effects? Like my program touches memory somewhere, allocates memory, or maybe not. Is that part of the input and output? Now, what about other requirements? I did a lot of talks about real-time and low-latency programming. So there you have requirements like this function must return within a millisecond or X amount of time, and if it doesn't do that, it's not correct, right? So there's lots of requirements here on program correctness. And some of them are also not doing certain things, like, for example, do not touch this piece of memory, or do not launch nasal demons. How do you reflect that in the specification? So it's a bit messy. So here's a practical definition of program correctness that is kind of useful when you're dealing with all of these things. So we can say that there is a set of expectations on the behavior of a program. And it's all of the stuff that I just mentioned and probably more. Those are expectations you have. Maybe there's an intention that you have when you write a program, or a type, or a function, or a loop, or an algorithm. And so there is a set of expectations here, and some of them are explicit and others are implicit. And so we call this whole set of expectations the contract of that program, or that function, or that class, or whatever. And then, that contract has a bunch of parts. Like, we can talk about the essential behavior of programs or functions. So for example, if a function is supposed to sort a range, then the fact that it's sorting it is part of the essential behavior. Maybe if it allocates a buffer while it's doing that, it may not be part of the essential behavior because it may not care about that. Or it may be because you do care about that function not allocating any memory while it does that, right? So it can be part of the contract or maybe not. The computer doesn't know. The human does. So you have an expectation. Functions have preconditions and postconditions. Those are different aspects of the contract, right? So precondition is a condition that the function expects to hold when it's called. And a postcondition is a condition that the function guarantees will hold if it's called with the precondition satisfied and it does its thing, right? Classes have invariants, loops have variants and invariants, and there's other things. And so all of this together is the contract of a particular piece of code. And the correct program or function or class is one that satisfies its contract, okay? So that's the definition I'm going to be working with. And so the flip side of this last bullet point is that a contract violation, a failure to satisfy the contract, is always a bug. So it's something where your program code is incorrect. And the way to mitigate that is to go into your code and fix the bug. All right. So a contract has many parts, as we just saw. Like, some of this is implicit. There are coding conventions. There's common sense. For example, often there is a contract that a const member function should be thread safe, right? That's not something you typically write down, but in some code bases, in some companies, people have that as an expectation, as an example. Others are explicit. Often people put that into their code comments. This function, returns blah, and it's undefined behavior if you don't do blah. Or in a separate document. We do this in the C++ standard itself. For every function in the standard library, we say these are its preconditions, these are its postconditions. And then we can also do this in code directly in C++. And that's what we call contract assertions, okay? And this is something that before C++26, we could do this with cassert macros or with user-defined assertion macros. And since C++26, we have a proper C++ language feature to express contract assertions. So we got 3 kinds of those in C++26, pre, post, and contract assert. And so those are, that's what contract assertions are. They're a way to specify aspects of the contract, of the expectations in code. Now, some people, when they mean contract assertions, they just say contract. Contracts do this, contracts do that. And what they actually mean is contract assertions. That's kind of not correct. When we say contract, we mean the whole thing. But kind of to disambiguate that, we can say that the whole thing is the so-called plain language contract. It's the thing that's formulated in plain human language. And then contract assertions are this bit here, and by their nature, they can only encode a subset of the plain language contract. There's always going to be aspects of that, or in most cases, that you cannot express in contract assertions. So to give you a few examples, if you have a kind of vector-like class that you're implementing, you can now add a precondition assertion to that code. For example, if you have your bracket operator, you can add a precondition assertion that the index is within bounds. Right, so that's great. So if you check that precondition, then that's going to catch a lot of bugs. So that is written down actually explicitly in the code. You don't have to talk about parameters there in the precondition assertion. You can also talk about other state. For example, front, you can write a precondition that the vector is not empty. It's a bug to call front if the vector is empty. It typically leads to undefined behavior according to the standard. if for std vector, you can do something else, of course, in your own vector. So there's clear. Clear has a post condition, so you can write that as a post condition assertion that the vector is empty afterwards. And one thing that you can do with post condition assertions that you cannot do with macros is you can directly refer to the value that the function returns. We have a little bit of a syntax there with this colon. So for example, for empty, you can say that it returns true if and only if size is 0. So you can write these post condition as precondition assertions, and when you write them, it doesn't actually necessarily say anything about what's going to happen at runtime. You're just expressing your expectation. What happens at runtime is something you can configure. So with certain macros, you can turn them on or off. With C++26 contract assertions, you have a few more options. We have 4 contract semantics in C++26: ignore, observe, enforce, and quick enforce. So you can choose whether or not you want to check the predicate. And if you check it, you can choose whether or not, if the check fails, you call the contract violation handler, which is a function that does something like printing a log message. And you can also choose whether or not the program should terminate instead of continuing. And so these 4 evaluation semantics give you those options, and they kind of cover all of the common use cases that you might want to be covered, depending on what you're doing exactly. One more thing is that which semantic is actually used is implementation defined. So that's not in C++26 directly present in the code. It is actually typically going to be controlled by a compiler flag. And then finally, the violation handler, which is the function that's going to be called if you use observe or enforce and check fails, you can replace that at link time. The way you can replace operator new, operator delete, you can specify your own. You just need to specify a function that has the signature and do your own contract violation handling in there and then link that in, and that's going to work. Now, remember that this is only there to express a subset of the plain language contract, right? So this is very, very useful, but there's a few things we cannot do with this, or we cannot do yet with this, or we cannot do with this in principle. So, for example, operator bracket also has a post condition, and the contents of the vector are the same as before after you call this, right? And so this is a post condition that you can express in code, but it would get very cumbersome. You probably don't want to do that, and you don't want to check that. It's often not practical to do, so you just don't write a contract assertion for it. You just kind of leave it as part of the plain language contract. Another example is pushback. Who can tell me the contract of pushback? Guy?
Size incremented by 1.
Size incremented by 1. Something else?
Non-empty afterwards.
Non-empty afterwards. Something else?
Last item is the item back.
Yes, the last item is the back item. So this is something we can already write. But the one that size is plus incremented by 1 afterwards is something we cannot write yet in C++26 because we need to refer to the size that the vector had before we called the function. So we need to have a little bit of an extra syntax here to capture that old size. This is syntax that didn't make it into C++26. We are hopefully going to have this in C++29. And then there's a third post condition, actually, which is
The rest of the elements are the same as before.
The rest of the elements are the same as before, yes, and there's one more.
There are no iterators that are different.
So there is a thing called the strong exception guarantee. So if this pushback doesn't actually return, but it throws an exception, then the vector is unchanged, right? So this is not something we can express right now because post only talks about what happens when the function returns. We don't have a syntax to express for what happens when a function exits via an exception. So this is again something we hope to be able to do in C++29. We have ideas how to do that, what the syntax for that could look like, but it just didn't make C++26. Another one that people are asking for is class invariants. It would be very nice if you could write this or express all the other class invariants in this way. Again, we're hoping to get that into C++29. We don't have it in C++26 yet. And then there's another type of contract assertion, which is things like, if you are dealing with a range, begin and end, there's a precondition there that is actually a valid range, and you're not passing in, dangling pointers or pointers that point somewhere where they shouldn't be pointing. So that is very interesting. That's a common source of bugs, but we don't know yet how to express that in C++. So for this stuff, contract assertions are probably not the correct tool. So we're going to talk about that a bit later. So here's a bit of a summary. So what contract assertions are, they're a syntax to express the human user's expectations on a function's correctness, right? So they express a subset of the contract of a function. So they're optional and runtime checks of those expectations. So both of those words are really, really important. They're optional, you can turn them off. And it happens at runtime. And you can mitigate violations. They're portable, scalable, freely configurable. Those are all things that are now much better than they were with macros. They're not just for runtime checking. So a static analysis tool, for example, can consume the pre and post conditions and derive information from them. So it will help static analysis as well. An IDE can consume them and then display you a nice bubble. You know, if you call this function and it has a precondition, a post condition, you get like a nice bubble saying, hey, there's a precondition here. And maybe that's then also coupled with the static analysis tool that can sometimes derive information that maybe you violated that because you passed in something that doesn't fulfill the precondition. It can tell, you know, statically that that's the case and display you a little squiggle or whatever. So that's going to be very useful for other tools, not just for enabling runtime checks. And they are a superior replacement for assertion macros. They have many, many advantages. I've given talks about contracts specifically where I talked about those things. You can put them on declarations, so that can go into a header. That's a big thing. You know, a macro can only go into the body. So anything that only sees the header cannot see them. But if they're in a header, everybody can see them. The compiler can see them, the human can see them, the IDE can see them, etc., etc. You can refer to the return value directly in the post condition. Again, something you cannot do with macros. There's lots of other stuff. And one really important property of contract assertions is that they are redundant in a correct program. So if your program is correct and does fulfill its contract, then contract assertions do nothing useful. Right? They're only there to identify cases where your program is incorrect. And that's why it's really important to have this property that you can turn them off, because if you're reasonably confident that your program is correct, you don't want to pay the runtime cost for those checks. So you need the ability to disable them. That makes them very different from things like, you know, if statements, where if this happens, you do this, otherwise you do that, and that's just an unconditional thing, right? So that's very, very different here. And that leads me to what contract assertions are not. Contract assertions are not a tool to prove correctness, because in general, you cannot do that, because they cannot express the entire contract, and B, typically that's not something you can prove unless, you know, in specific cases. Contract assertions are also not a tool to express something that isn't part of the plain language contract. So they're strictly there to express correctness expectations. In particular, it means, a corollary from this, is that contract assertions are not a tool for error handling, because there's a difference between an error and a bug. An error is something where something unexpected happened, you want to handle that. A bug is something where the only way to handle that is to fix your code, right? So those are, you know, categorically different things. If you know, you have a program where an error could occur, like invalid input or something unexpected happens, you want to handle that unconditionally. No, you don't want that to be handled by something that you can turn off, right? You don't want that. And also, an error that you handle doesn't mean that your program is buggy, right? So we need to distinguish bugs and errors, and we need to distinguish error handling from you know, finding bugs, and contract assertions are definitely the latter and not the former. And one more thing, contract assertions are not a tool to provide language level guarantees, right? So they only do something if you add them to your code, and they don't change the behavior of existing code. So if you're looking for things like, you know, my operator square bracket will never have undefined behavior, you know, that feature can't do that, because A, you have to actually put the contract assertion there, and B, you can't rely on it actually being checked, because it's really, really essential that people can turn it off. So if you want guarantees, contract assertions are not the tool for that. We're going to talk about that later as well. Contract assertions are aiming squarely at this correctness bubble here. So they're a way to not prove correctness, but improve the correctness of your program and identify cases where the program is not correct. And while you can never prove that your program is correct, your program is going to be more correct with every contract assertion that you add to your code, right? So with every conditional assertion you add to your code, you're going to incrementally find more and more bugs, making your program more and more correct. So that is a property that you can only approach asymptotically. You can never actually say that my program is correct, unless, in very specific cases, which is the whole proving aspect that we're not talking about here. So we talked about correctness. Let's talk about safety and security. So those things received quite a lot of attention in the last few years. And let's start with safety. That is a word that you hear a lot. Safe, C++, safe code. We want to make something safer, or something is not safe. So on the C++ committee, we have a big desire and a big push to make C++ more safe. That is a great thing. A lot of people are working on that. However, progress in this has not been as quick and as effective as I would have liked, maybe, or some people would have liked. And I think one of the reasons is that it turns out, and we lost a lot of time actually on the committee because of this, different people mean very different things when they say safe. And I heard, people in the C++ committee or otherwise in the C++ community mean at least 4 different things when they say safe. Right? So, and the problem is that one person says, this should be safe, and they mean one thing, and another person says, well, but this isn't safe, and they mean something else, and the 2 people don't realize that they mean different things. And so that means there's a lot of miscommunication that makes the whole process very inefficient. So one definition of safe, which, for example, Dave Abrahams mentioned in his C++ Now keynote a couple of years ago, is that a safe operation is one that cannot cause undefined behavior. And by that, he means the kind of unbounded undefined behavior that we have in C++. Right? The compiler can do anything. You don't know what's going to happen. And a safe language has only safe operations. And so this is the definition that I think people mean most of the time when they say C++ is not safe or a feature is not safe. They mean it has UB or it doesn't have UB. And a lot of the discourse is focused around that. And whenever we talk about memory safety and type safety and initialization safety and all of these other safeties, typically it happens in this context of those are types of UB that we want to avoid. Right, so that's one definition of safe. That's actually very, very, very different from what most people outside of C++ bubble actually mean when they say safe. Right? So the definition of safe that most people out there use is that something is safe if it doesn't cause harm to people, equipment, or the environment when something goes wrong. Right? That is what we normally mean when we say safe. Right? And so there is yet another definition, which is kind of rooted more in safety critical code, which is, so we have on the committee actually a study group for safety. And when that study group was founded, they released a paper, like a mission statement with lots of people's names on it. And in that paper, they defined what safety is for that study group on the C++ committee. And that definition read like this. Safety is an emergent property of systems measured statistically and regulated by policy. The prerogative to decide if something is safe is usually reserved by governmental organizations. Right, so that is yet another definition of safety, which is the one that is very similar to what is used when you look up safety critical code, kind of regulations, ISO standards about safety. This is kind of where this is going. And then there's a fourth one. So Chandler touched kind of on this in his definition a couple years ago at C++ Now, when he said, safety is characterized by invariants or limits on program behavior in the face of bugs. But really, I think Sean Parent explained it very clearly, I think 2 years ago when he was giving a keynote on this stage at this conference. So Sean Parent said that the safety of a program is a set of safety properties that hold given valid input. And a safety property is one which states that something will not happen. For example, his example was a self-driving car will not go off the road. Right? That is a safety property. And the safety of a programming language is a set of safety properties guaranteed for any expressible program. That was Sean Parent's definition. So that goes into something that's called Lamport properties. So Lamport actually developed a framework in the 70s, which was built on Hoare logic, where he says that a program is correct if it satisfies liveliness properties and safety properties. And liveliness properties are there's a guarantee that something will happen, and safety properties are there's a guarantee that something won't happen. And the combination of that gives you correctness. So that is, again, a different take on it, which is kind of taking place in a kind of more mathematical framework. You can then prove these properties in certain cases. So, all of those things are interesting and valuable in a certain context, but the problem is that we keep talking past each other. So my suggestion is that we actually say what we mean. So all of those concepts actually have names, right? So the first one, we can call it functional safety. This is what people in the safety field usually call this. The second one is usually called system safety. The third one, I have personally called it language safety in the past. I actually don't think it's a good term now because it kind of interferes with the fourth one a little bit, which also talks about languages. So I think I'm just going to call this absence of UB because that's what it is. That's what we're talking about. Is there UB or not? Can there be UB or not? So let's just say what we mean. And finally, the fourth one is kind of Lamport's framework. So we should call it Lamport safety or something like this. And when we just say safe unqualified, I think we should always put it in quotes or maybe just not use it at all. Let's just not use the word safe unqualified because this is just prone to misunderstandings and talking past each other, and a lot of time has been lost in these miscommunications. And one more distinction that we need to make is that the rightmost two also distinguish between a program that has that property or a programming language that has that property, right? So there's a difference between does a program have UB and does a language let you express programs that have UB, right? So we need to distinguish that as well. So let's call things by their names, and I think that's going to improve the discourse about safety quite a lot. So let's talk about how these things kind of interfere with each other. Like the one example of where kind of these four things, they kind of overlap, but they don't coincide. So for example, there is this kind of tension between functional safety on the one hand and absence of undefined behavior on the other side. This is a particularly common source of people talking past each other. So absence of undefined behavior, I think we all agree is a good thing, right? Because if you have undefined behavior, that is always a bug. So your program is always not correct. So it always doesn't satisfy the most important property to satisfy. So UB is bad, absence of UB is a good thing. However, absence of UB is actually not a necessary condition for functional safety. And we know this because people have been writing safety critical code in C++ for decades. There are things like regulations and certifications. There's testing and code reviews and all of these other practices, right? There is tooling around this. So people have been doing this for decades. You can write safe code in C++. We know this because people have been doing it. And on the other side, absence of UB is also not a sufficient condition for functional safety because there's lots of safety relevant bugs that actually have nothing to do with UB and nothing to do with the programming language at all. For example, let's imagine you want to build a rocket that flies from here to over there. And then somewhere in the algorithm that calculates where the rocket is flying, you keep adding floating point numbers to each other, right? 1,000,000 times. And then you fail to account for the fact that floating point works in a certain way. And if you add a floating point number to another floating point number 1,000,000 times, you're going to have accumulating floating point errors, which you need to correct for. And if you don't do that, your rocket probably is going to fly somewhere entirely different, right? So we got this Mars probe that crashed because people used the wrong units, things like that, right? So there's all safety critical bugs that have absolutely nothing to do with UB or with your choice of programming language. They have something to do with business logic, right? So this is somewhere where testing helps, where context assertions can help, where getting rid of all the UB in the language is not going to do anything for that, right? And then let's talk about security because that is kind of related to that. And luckily here, we don't really have much of a disagreement. I think we all agree on what security means. So when safety is more about something that can go wrong accidentally, then security is all about malicious attackers, right? How well is your program protected against malicious attackers, and what are the limits on what a malicious attackers can do, and what guarantees do you get? So here it's a little bit different. Absence of undefined behavior may actually be a necessary condition for security, and I mean here the kind of unbounded UB that we have in C++. Because if you can have UB, then somewhere you will have UB, and then somewhere somebody can exploit that and get remote code execution or something else. We have lots of examples about this in the wild. We have lots of CVEs that are exploitations of UB. So absence of UB may be necessary for security. It's certainly not sufficient, right? So many security vulnerabilities, again, have nothing to do with UB. And there is this commonly cited number that 70% of CVEs in C and C++ are caused by memory safety bugs, which may be true, but it doesn't mean that if we somehow magically make C++ memory safe, then we're going to get 70% less attacks. And Herb Sutter wrote a blog post about this, which was very good in my opinion about this. So malicious attackers, they're like a gas, right? They fill all the available volume. So if you kind of get rid of 70% of the vulnerabilities, then they're going to focus on something else, right? So I'm not want to downplay the importance of addressing undefined behavior. I just want to talk about the fact that it's not going to magically solve all our problems. And there's been maybe a little bit of a focus on undefined behavior under the impression that it somehow magically solves a lot of problems, and it improves a lot of things, but it doesn't magically get rid of them, especially when we talk about safety and security. So we talked about what is a good program. So we realized that safety is actually 4 different things, at least. So we need to talk about which one do we actually mean. There's one more thing I want to point out, which is the correctness one up there. So the way we define correctness, a program that has a safety bug is certainly not correct. A program that has undefined behavior is certainly not correct. A program that lets a malicious attacker do something bad is certainly not correct. So actually this diagram should be more like this, right? If a program is correct, then by definition, it's also safe and secure under all of these different definitions of safety, right? So, and contract assertions target this big bubble there. They help you make your program more correct. And this is the connection between contracts and safety that people have been arguing about so much. This is kind of how it fits together. Now, of course, contract assertions and other things can help you find bugs and make your program more correct. But as I said already multiple times, you can never know that your program is correct. So then you still do need to make sure that when your program is not correct, there is a limit on what can go wrong when that happens, right? So we do need to tame the nasal demons of undefined behavior because that will help a lot with those things. But it's not something that we should do instead of contract assertions, or that somehow is 2 different ways of doing the same thing. It's more like the Swiss cheese model, right? So all of these things are different slices of cheese, and hopefully the holes don't align but are in different places. So when you have a problem, if one slice of cheese doesn't hit it, the other one will. So this is how I see kind of the effort we went through to get contract assertions in the language versus the efforts to reduce the amount of undefined behavior in C++. Those are both important, but they're complementary, right? They help each other. So let's talk about UB, because now that we have contract assertions in the language, that's kind of the next thing that I'm personally focusing on. I want to reduce the amount of UB in the language. So something that people commonly say, and I read this regularly on the internet, is, well, so we have all of this UB in the language. Why don't we just all make it all informed? How is that not the solution? Now that is more interesting actually than it seems. So why can't we just do that? The answer is, of course, well, UB is a runtime property, right? So you cannot actually prove at compile time in most cases, whether an expression will have UB or not when you actually run it, right? Because that depends on runtime data that you don't know at compile time, right? So all you can do is you can say, well, I don't know if it's going to have UB or not, but if it could, then I'm going to make this whole feature ill-formed, and then you're going to break a lot of existing code. So that is kind of the fundamental problem here. So memory safety is particularly difficult in that sense. And this has been studied for a long time, and there's a certain amount of known approaches to memory safety, right? There's runtime approaches and compile time approaches, right? So runtime approaches, we know that from Java and similar languages, there's garbage collection, which gets rid of the use after free problem. There's reference counting, like Swift 6 does this, I think, for example, where everything's just by default reference counted, which also gets rid of that problem. Doesn't get rid of all the problems, and it also has particular trade-offs in terms of performance and other things that we don't want in C++, right? So then the other approach that we do use in C++ is sanitizers that inject a lot of instrumentation to track this information at runtime, like what the memory points to, what type is the object where that memory points to, et cetera, et cetera, et cetera. And those things are effective. They don't catch all the errors. In particular, when it comes to thread safety, the coverage is not very complete. And also, those things have a massive runtime overhead in terms of size and also in terms of just runtime, right? So probably in most cases, we don't want to run those things in production. So they don't give us a guarantee. They help us find bugs, but they don't give us a language level guarantee. If you want a language level guarantee, then the only compile time approach that we know of, to my best knowledge, is to somehow enforce what we call the law of exclusivity. And I think John talked about this in his talk yesterday, where if you have a mutable reference to an object, you need to make sure at compile time and design your language that way that there can be no other reference to that same object at the same time. You need to ensure that this never happens. So you end up with something very similar to the Rust borrow checker. There's other models that are subsets of that, like Hilo's mutable value semantics, or functional languages where you can just not mutate anything at all. So we could do that, right? But then none of the existing C++ code could compile, right? You would have to rewrite everything. And that is, to a first approximation, the only way to get rid of UB, those things, right? There's not really much else we can do. So making C++ memory safe isn't really a thing we can do unless we want it to become an entirely different language. That is just the reality, right? But also the flip side is that we actually need unsafe code for some things, right? Rust has unsafe Rust, and you need to implement certain things in unsafe Rust. For example, if you enforce the law of exclusivity, you can't implement a W linked list. That's just not possible. You can't call certain C functions like syscalls that you just need to call in order for your program to do its thing. So this works in Rust because in Rust we have this kind of big set with code that and I very much resisted the temptation to say safe, not safe here, because in Rust those things mean something, but in C++, as we saw, it can have different meanings, so I resisted that temptation. I wrote code with no UB, which is like Rust by default, and then you have these islands of unsafe Rust code that may have UB, but they're small enough that you can look at them, reason about them, and if you get it wrong, you know where the problem is, right? So this is a great world to live in. Unfortunately, in C++, our starting point is this, right? So this is where we're starting. So how do we get from here to here? Well, it's not really something we can practically do, right? So I think some people maybe fall into this trap of doing something like this, where they say, well, we should do what Rust does. But I don't think that makes sense. If you need language guaranteed memory safety, then use Rust, because that exists. That's what it's for. And we cannot achieve that in C++. But if you want to support your legacy C++ code, then you will need to continue to write C++. And this is something that we will keep doing for decades because the world runs on C++. This code is not going anywhere. So we need to deal with this, but not by saying it needs to be like Rust, but by doing kind of the salami tactic, right? We kind of can't eat the whole salami in one go, and maybe we can never eat the whole salami, but we can do it one slice at a time. Let's remove a little bit of UB here, remove a little bit of UB there, and asymptotically reach a better place. And I think this is what we need to focus on in the C++ community. And so there's things that users can do, and they have been doing for years. There's things tooling vendors can do. And then there's things the C++ committee can do, which is systematically address UB in the standard. And this is something I want to focus on because as a member of the committee, I do have some impact there. So I can, together with other people, actually make this happen, right? To do something to really move the needle there. We can't get rid of all the UB for everybody, but we can make the situation a lot better. And so we have actually been doing this on the committee for a while. So we have systematically reduced the amount of UB. In C++20, we introduced implicit lifetime types, right? So now if you cast a pointer to a buffer to an object that you haven't actually constructed, it's no longer UB under certain conditions. In C++23, we fixed the range-based for loop thing, which caused a lot of bugs in UB. And in C++26, as Herb said yesterday, we're introducing kind of well-defined behavior for some forms of uninitialized reads. Those are all good things, but those are kind of case-by-case things, right? So what we really need to move the needle a bit more significantly is a systematic and holistic approach. And this is kind of, we just started doing this, but it is something that I feel we really need to take seriously and tackle and focus on. So earlier this year at the committee meeting in Hagenberg in February, we kind of agreed on pursuing this white paper, how are we going to systematically address UB in the language. So this is kind of a bucket where you want to put different things. And there is one paper, P3100 R2, which I've been working on for a while now, but together with my colleague Joshua Byrne, to do a systematic treatment of poor language undefined behavior in C++. And this thing that the committee voted for lists as possible tools erroneous behavior, profiles, and contracts as things you might want to work on. So here we're focusing on erroneous behavior and contracts. Profiles is something that other people are focusing on. So those are, again, complementary things. And so the goal of this paper is to introduce a standardized framework for runtime, right? Remember, compile time and runtime, they're complementary. Runtime detection and mitigation of undefined behavior across the entire C++ language. And this is kind of a piece of work that I want to spend a little bit of time talking about. How are we doing on time? Okay, good. I'm about halfway through my slides, about halfway through my time, so I think we're good. So what's in this paper? We did a lot of work. We actually went into the standard, grabbed for every occurrence of the word undefined, and looked at each one of them very, very closely. We enumerated all cases of explicit core language undefined behavior in C++. So we didn't look at library UB, like that's another topic. We have library hardening for that in C++26. That's another tool that I'm not going to be talking about. But we looked at all the core language undefined behavior that's explicitly called out, enumerated it all. It's all in a big appendix of this paper. There's like 20 pages, which is just a big list. We gave them all unique identifiers, so we can refer to them. And we grouped them into 12 categories. And then we classified each one of those cases according to a bunch of criteria. Is this one relevant for security? Is this locally checkable? Or maybe it needs global instrumentation to check, right? Like some things that sanitizers are doing. How expensive is it to check it at runtime, undefined at runtime? And independently of whether we want to check it or not, is there anything we can do to replace the undefined behavior with well-defined behavior? So if that thing goes wrong, can we then say, instead of the behavior is undefined, this other thing happens instead, right? So we identified all cases where you can define a behavior like this. So we already have one in C++26, which is the erroneous values when something is uninitialized. That's wrong, but well-defined. So we identified basically all the other cases of UB in the language where you can do something like this. And we classified them according to possible mitigation strategies, like compile time detection, runtime checks, defining a well-defined fallback behavior, et cetera, et cetera. And then we have a proposal with wording for how to add these things to the standard. So that's a huge chunk of work. We reviewed that in multiple subgroups of the committee over the last year, and then finally last week at the committee meeting on Sophia, it was in the evolution, language evolution study group. They really like this, and they want to go ahead with this approach. So this is hopefully going to go into this white paper. So we identified 90 cases of explicit language UB in the standard. That's a lot. They fall into 12 categories. So those are the 12. Type and lifetime is one category because we found that although type safety, like something you're accessing memory through reference of the wrong type, And lifetime safety, there's an object within its lifetime. There are different things. A lot of UB falls onto a spectrum. Like some of them are clearly about type safety, others are clearly about lifetime safety, but many of them are kind of like, this pointer or this reference points to an object of the right type, and that object is within its lifetime. So you kind of can't like separate them. Arithmetic is all of the stuff like overflow, conversion to a different type where the target type cannot represent the value, all of that stuff. Threading is race conditions. Sequencing is things like I plus 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 I. Assumption is, assume false, double square bracket, right? That's undefined behavior. Control for are things like flowing off the end of a function or flowing off the end of a coroutine. Replacement functions, that's interesting. That's things like you defined an operator delete and that operator delete throws, things like that. That's undefined behavior, actually. Coroutines are things like, you kind of try to resume a coroutine that it's never been suspended or things like that. Templates is interesting. Infinite template recursion apparently is undefined behavior. And there's a bunch of preprocessor things that are undefined behavior. We actually fixed that last week, so I need to update that slide. So the cases of UB kind of fall into these categories not very evenly. It's actually the majority is in a type and lifetime category, while threading, for example, just has one case, which is the definition of a data race. Those three categories are the ones that are commonly associated with security vulnerabilities. It doesn't mean that the other ones are not important, right? Things like signed integer overflow or race conditions, they cause crashes, they cause bugs, they cause damage that you can name. There's millions of dollars, but they're not causing security vulnerabilities as much, right? So it means that we need to fix all of them or address all of them if we can, but there's kind of a difference in what is the kind of threat model here that we're talking about. Then we looked at which ones are locally diagnosable at runtime. So it means like for which could the compiler insert an assertion to check whether the UB occurs, and so then maybe terminate the program so it doesn't actually occur. Turns out for the majority of UB that's not possible. For about 20% it is possible. For about 8% it's possible sometimes, like array indexing into a C array or a raw array. Sometimes the bound is known statically, and then the compiler can check it locally. Sometimes the bound is not known statically, then you can't do that. And there's a bunch of these like 9%, 1%, 2% where runtime mitigation isn't the right thing to do. I'm going to talk about that later briefly. So for the vast majority of type and lifetime UB, you cannot diagnose it locally. The arithmetic ones you can, right? Because there's a value there. You can inspect, the compiler can inspect it. The compiler knows the bit representation. So it can do something about that locally. There's cost of diagnosis that falls into a spectrum. I'm not going to talk about that here too much. There's a paper you can go and read. The simplest one is, it's an error if you get here. That's like the simplest assertion that you can write, which basically has no overhead on the happy path, something like flowing off the end of a function. A compiler could insert something there. Then there's a null check, like null pointer check, integer comparison, that would be a bound check. And then it gets progressively more complicated and expensive. There's UB for you're trying to placement new an object into memory that isn't properly aligned. And then you can insert a check whether the memory is properly aligned. That's probably modular or something a bit more expensive. So there's a spectrum here. There's also the question how often you would have to insert that check. For not locally diagnosable UB, the cost is dominated by the kind of extra instrumentation that's not available within the C++ extract machine that you would have to insert. If you want to catch all the type and lifetime UB in the language, you would have to track all of these things somehow, right? So that is probably an order of magnitude runtime overhead if you want to do that, which is one answer to the question, why can't we just do that, right? Then, for other categories, for threads, you would have to track all potentially concurrent access to memory. That's probably not feasible, but something like ThreadSand can do it partially in some cases. That's useful, that's good, right? And then well-defined fallback behavior. So I'm not calling this erroneous behavior. It's conceptually the same thing. This is something that happens and we know it's incorrect, but it's not UB. I'm not using the term erroneous behavior because that is very specified in a very, very specific way today in the C++26 draft. And I don't want to say that I mean this exact specification because that actually has problems. So if you want to integrate this into this bigger framework, we need to tweak it a little bit. So we need to generalize it a little bit. And so if you want to replace UB by well-defined kind of fallback behavior, this is wrong, but it's still well-defined, then that cannot depend on whether we know that the error in fact occurred. It needs to be something where the compiler can just unconditionally insert an instruction that does the wrong but well-defined thing, regardless of whether the UB will actually occur, because you don't know that at compile time typically, right? So it turns out for 14% of cases of UB in the language, you can actually do this. For the majority, you unfortunately cannot. If you dereference a null pointer, there's nothing you can do after this to keep going that is well-defined. The only thing you can do if you diagnose that is to terminate the program. Right? That's pretty much your only option. So there's 17 cases of UB for which well-defined fallback behavior is definable. Most of them, like all of the arithmetic stuff, is kind of return an erroneous value. There's a few other things we can do with the other ones. For example, if you want to have race conditions that are not UB, Java has a model for this, right? All primitive memory accesses are implicitly atomic. This is obviously going to have a lot of runtime overhead, so we don't want to just do this unconditionally, right? So we can notionally define it, but it needs to be something where you can opt out of that, right? You can't just say this is the behavior for everybody all the time, because that's going to be unacceptable runtime overhead for many people. So there's a few other interesting cases. Infinite template recursion, we can just make that all formed. Preprocessor UB shouldn't be UB, it should be IFNDR, and we actually made that change last week. That's this paper P2843, which you have approved for C++26, I believe. There's a case that is not actually introducing any new UB, it's just talking about UB that's defined elsewhere, so we can just fix that in the wording. Then there's another one where we can just say it terminates unconditionally because nothing else makes sense. The remaining 79 cases is runtime DB where we cannot do anything about it at compile time. And so for those things, we can do two things, right? We can insert a runtime check, and we can, where possible, and we can define the behavior that happens afterwards if the check fails, if possible. Of course, termination is always an option. I'm not counting this. I'm counting other behavior that happens if you didn't even do the check, right? That's not undefined anymore. So those two are kind of the runtime things we can do. And so this is what the actual proposal in the paper focuses on. So it consists of three parts. One is systematically introduce runtime checks whenever we can define them. Part two is systematically replace UB with well-defined behavior. And part three, because that often has runtime overhead, provide an opt-out. The first one basically is based on contracts. So we already saw this, right? So you can write a precondition assertion like this. We call this, and so this is just a refresher. This is evaluated one of these four possible semantics. If it's checked, we can call a violation handler. We can terminate the program or not, depending on how you configure things. And we can install your own contract violation handler. So we now say that these things that you add yourself and you write pre-blah, we call them explicit contract assertions. So that's kind of what's in C++26. And now our strategy is that we allow the compiler to inject implicit ones. So whenever it's possible to detect a case of UB by inserting a runtime check implicitly, we just say that that check is there, right? And then it's a contract assertion. So in every other way, it behaves like a contract assertion. So it can be ignored. So the compiler doesn't actually have to insert the check. It can just do what it does today. But notionally, the contract assertion is there. So it can be enforced, ignored, observed, quick enforced. So basically, we propose to add this transformation to the entire standard. Whenever it says, if X is not true, the behavior is UB, we say, operation A has an implicit precondition assertion that X is true. So we basically just apply this wording transformation to the entire stack. And so that inserts an implicit contract assertion, which behaves in every way like an explicit contract assertion. So if you turn them on, you get a contract violation handler call, et cetera, except that they are implicitly generated by the compiler, right? So we do not require an implementation to provide all possible checks because that's just not possible, right? We cannot expect that every compiler is going to be a super sanitizer that catches all the UB, and we cannot expect anybody to actually use that. But ignore is always a valid choice. So we define that these checks are there, and then the compiler can choose for which ones it wants to offer a check semantic like enforce, where the program terminates, right? And because the choice of semantic is implementation defined, that means that the implementation can actually has to document which semantic is chosen when, what the mechanism is to do that, right? So that allows us to bring all of the things that are already doing this today kind of into the scope of the C++ standard. So compilers have flags where they insert checks. Sanitizers inserts even more checks. And so then we can reason about those things with words that are defined in the C++ standard. It's no longer just UB and you can do whatever, but there's a portable standard framework, how this should happen. It enables things like every sanitizer calls into the same callback API instead of every sanitizer having their own. And that callback API is the standard contract violation handler API. It allows things like codifying names and categories for every single piece of UB in the language. And then, if your contract violation handler is hit, you can query, was this a bounds problem? Was this an arithmetic problem? And do something else. In each case, you have standard types and names in the language to program with these things. And that enables seamless integration with contract labels that I'm going to talk about in a minute, profiles, which is another syntactic thing that you can do, etc., etc., etc. So that's part one. Part two is systematically replace UB by well-defined fallback behavior. And so actually the transformation that we're proposing is this one, right? So if the fallback behavior exists, then we say, operation A has a precondition assertion that X is true, and if you violate that, you get that fallback behavior. You no longer get UB, okay? But then if the fallback behavior doesn't exist, then we go into the no branch, and then continuing execution is still undefined behavior because there's no reasonable behavior that a program can have if you continue past a null pointer check. But you can instruct your compiler to insert checks for null pointer and then evaluate it with the enforce semantic or the quick enforce semantic, which means that whenever that check fails, you just terminate. Right? That's something you can always do. And the third part is providing an opt-out, because you cannot just impose this well-defined fallback behavior on everybody unconditionally, right? And so the way this works is by introducing a fifth evaluation semantic. So we said we have these four, we actually have five. The fifth one is called assume. Do not check the predicate, but assume it is true. And if the predicate is not true, the behavior is undefined. That allows the compiler to optimize on the assumption that your contract assertion is true. And a lot of people wanted to have this feature in the standard for explicit contract assertions. A lot of people said, no, over my dead body, we cannot have this is not safe. So we ended up not having it for explicit contract assertions. And we're not proposing that we add that for explicit contract assertions. So the compiler cannot assume that your precondition, that the one you wrote, is always true and optimized based on that, because that means you could inject additional UB into your code, right? That's not something that we want to allow. But for implicit contract assertions, assume is already the default, right? So every implementation is already assuming that UB never happens and optimizing based on that assumption, or not, depending on your optimization flags, but it's allowed to do that already. So assume is already the default for all of the implicit contract assertions that this framework would add. So the only thing we're doing here is to say, and there is an option to preserve the status quo so you don't run into unacceptable performance degradations. But you can enable checks if you so desire, and if your compiler, sanitizer, whatever you're running, offers that. So quick example for the no branch here, out of bounds array access, right? So here we have an array. We read the index forms.cin, so we cannot reason at compile time whether it's out of bounds or not. And then we index into the array. And so basically what implicit contract assertion means is that we treat the bounds how do you call this? The operator square bracket, the implicit one for built-in arrays. We treat it as if it was a built-in function, that the compiler generates for you that does this. And then we say, well, this implicit compiler-generated function now has a precondition assertion that checks for the bounds, right? And so that can be ignored. Status quo today. It can be enforced. It can be quick enforced. The compiler can say, I can't do that. I only offer the ignore semantic. Or it can say, I only offer it if the bound is known at compile time and things like that, right? So these options, these 4 semantics, they map exactly to things that we already have today, right? So compilers and sanitizers already have ways to do these checks. We just don't have a standard language to talk about them. With this proposal, we do. And so the other branch where we have fallback behavior, the good example for this is signed integer overflow. So here, if we add 2 integers, we pretend that that happens with a built-in operator plus that the compiler generates for you. And then we pretend that that has this precondition, which is checking exactly for, does this addition overflow? And the compiler can either insert those checks or not, or do something else, right? And you can choose. So here, assume is the status quo. Ignore is something like GCC, the f wrap v flag, which just wraps around. So it says that it doesn't check it, but the behavior is well defined, right? And then enforce is something like ubsan, which calls a callback, which by default prints a bunch of stuff and then terminates. And then quick enforce is GCC's f trap v flag, which just immediately terminates, right? That's the safest thing. So this is what we propose in P3100. This is the transformation we propose to apply to the entire standard. Now there is a little piece that's missing here, which is there is another paper, P3400, which kind of builds on top of that, which gives you labels, and there it gets really, really powerful. So labels are things that you can, kind of, again, this is not in CSS 26, you're proposing this for CSS 29. Labels are things like here, where you can add like a little annotation to your precondition assertion or postcondition assertion that constrains the behavior or lets you do certain things. And so we just say that implicit context assertions also have implicit labels like this. And a label can define a standard name, so this identifier, so you know what UB happened. We can have labels that organize them in standard categories like bounds. And you can add your own. For example, the implicit checks can be bounds checks. And then you can say, I'm implementing my vector and my operator, square bracket, is also in the category bounds, right? And so then if you hit your violation handler and you ask, is it a bounds error? You will catch all of these cases. The other thing you can do is in-source semantic control. So you can say in code, I want this to always be ignored, always be enforced, or never enforced, only observed, or other things like that. And there will be some syntax, like we don't know yet exactly what it would look like, but it could look something like this, where you say, in this file, in this program, in this class, in this function, in this scope here, turn on all the implicit context assertions that have to do with arithmetic UB, and make them always enforced, which means that the compiler has to insert the check, and when the check fails, it has to terminate the program. And if it can't do that, then you're going to get a compiler error, right? If the compiler doesn't support these checks yet. But compilers already do, so I don't think that's going to be a problem. So what we can do with this model is, we cannot get to the nice Rust world, but we can get from this world to this world. And then we can grow these bubbles over time, both in size and in like what UB is covered and no longer UB. And I think this is kind of the trajectory that we're on. So this is a particular piece of work that we did. How does it fit into the bigger picture? And this is something we spent a lot of time discussing last week at the committee meeting. We have all of these things, context assertions and standard library hardening, which builds on top of that, which is now in CSS 26. We have erroneous behavior, which is in CSS 26. We have the borrow checking stuff that Sean Baxter is doing, which seems to be just happening completely outside of the standard committee. You have a lot of people who wrote a lot of papers about profiles. Different people have different ideas what profiles are. There's a lot of other safety and security related papers here. How does it all fit? And so remember, this is the big picture here, right? And so now we're talking about just this bubble here. But it's a really, really, really important bubble. And so how do we get there? How do we make that bubble bigger? And so here's kind of the roadmap. There's legacy code you can't touch, and we need to do something with that. And there is new code that we're writing today, or code that we can actually edit, we can do something with, we can update, right? And so we identified different strategies how to mitigate UB depending on which half of the slide you're on. Are you dealing with code where you can make code changes, or are you dealing with code where the actual code cannot be changed at all because you don't own it, you can't touch it, whatever reason? So depending on where you are, there's different strategies, right? So for new code, you can do language subsetting. You can say certain things that may or may not have UB are just not allowed anymore. Like, for example, disallow C-style casts, disallow reinterpret casts. You have to do something else instead. Or explicitly opt into the unsafe features. Another thing you can do is annotations, right? So I said that a lot of stuff like, whether pointers are valid, whether references are valid, all of this memory safety stuff is not locally checkable. But you can make it locally checkable by adding annotations that kind of make this information about, what a pointer points to, travel across kind of boundaries. And so, for example, Clang has this experimental attribute counted by, where you can put that on a pointer and you can say this pointer points to an array of size n. And if you put in that annotation, that information will travel to other translation units in other parts of your program, and then the compiler will be able to insert a bounce checks there, even if you have array to pointer kind of decay and it's just a pointer pointing somewhere. Obviously, that allows you to actually add the annotation. So that means new code or code where you can add these things. Another thing you can do is just replace unsafe features by new features, like borrow checking. Or for example, instead of having just integer addition, which can overflow, we can have things like std add saturate, or instead of just casting an int to a smaller int, and then if it doesn't fit its UB, we can have std saturate cast, right, where it has defined behavior always. So those are things we can do with new code. If you can't touch the code, we can't do those things, but we can do other things, right? We can just redefine the behavior unconditionally. We can say, in certain cases, those cases are actually rare, and I think we've actually done most of them already. So I don't think we're going to find many more of those, but there's maybe a few left where we can just say that UB is just this other thing instead. We did that, for example, most recently for the range-based for loop lifetime extension of temporaries thing. Then we can do erroneous behavior, which means, it's not always this behavior which is now just well-defined and correct. It is still incorrect to do this, but it is well-defined. This is what we did for initialized reads. And then finally, we can say we insert runtime checks, and we now have a fully fleshed out framework for how to do this, which the committee or the evolution working group already voted to pursue. So this is kind of our menu of tools. And this is how we want to address UB in the language. So those two is what P3100 is proposing to do. This is our paper, the one that I just talked about. Language subsetting, this is another paper by Peter Bindels, which is talking about, what does that mean, how you define language subsetting, blah, 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 like all of the details of how you would actually specify that, and then identify these sets depending on, what compilers can actually do, et cetera, et cetera, et cetera. And now there's one thing missing here, which a lot of people have been talking about, which is profiles. Lots of papers have been written in recent months, especially about profiles and a framework to do profiles, and let's add profile, this profile and that profile. And it again seems like with the safety thing that different people mean different things when they say profile, and they have different ideas of what profiles should or shouldn't do. And we had a lot of disagreement about that on the committee recently, partially because profiles are not quite as fleshed out yet as some of these other ideas. So there's still work to be done there. And so some people say that profiles should be doing these two things, right? Runtime checks and language subsetting. So that puts them in conflict with P3100, which is kind of trying to do the same thing. So that kind of, we don't want to have two different ways of doing the same thing, maybe with different syntax. That's not good. So some other people said, well, no, profiles shouldn't be doing any of the stuff that P3100 does. Profiles should be just a syntax for language subsetting. And so, there was a lot of disagreement about that. But actually last week, and we actually did come to an agreement. So observe that the middle two ones are things that need to be configurable. Right? Runtime checks can be turned off or on, and you really need that to deploy them. And the same language subsetting is something that we need to be able to opt out of, so we can actually compile code that uses those features that you might have subsetted out because they're no longer considered safe. And so really, profiles, the role of profiles is to be named configuration presets for things below, right? So ideally, a profile name just expands to a bunch of statements about evaluate these runtime checks with this semantic and like apply these language subsets. And that's what they are. And this is something that we discussed for a long time and agreed with some of the authors of the profiles paper present, and we had good discussions about that. And so that's great. So, next time somebody asks you, so what is the committee doing about all of this UB in the language? It's a big problem, and they don't know what to do, and there's no plan, and there's no strategy. No, 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 no. This is our plan. We have a plan. This is our plan to address UB across the entire language. And this is what we're going to be doing for the next few years. All right. So that concludes the technical part of my talk. Now, I do have a little bit of time left. So we can talk about cats. So one other thing that I notice a lot of people in the room, myself included, tend to do is when we talk about these things, we tend to pretend that the technical issues, which is everything I've just talked about over the last hour, that's the main problem. That's what we need to focus on. We just need to solve the technical issues and then we're good. Turns out that's not the case at all. That's part of it. But a lot of the time, a much, much bigger problem is the people stuff. How do you actually agree on something? How do you communicate? How do you make a decision? How do you organize the work? And in the couple of years that I've been very intensely focused on contracts specifically and some of these other things, I've recognized that this is the real problem. This is the thing that actually holds us back. So to use this cat metaphor, for example, you have these cats, and the cat in the middle wears a hard hat, and the cat in the middle is really convinced that everybody should wear a hard hat because that's the way we do stuff, right? The other cats, they don't really agree. They don't want to wear hard hats. But then the other cats, maybe they have other ideas what to do. And then the bottom cat doesn't really care about any of that and just wants to go for a swim. And the other cats don't get that because they're afraid of the water. And so how do you make these cats agree on what to do, whether to wear a hard hat and whether to ban swimming and what else to do? And it turns out that is very, very, very hard. And so the reason that standardizing contracts took 21 years from the first proposal to it being approved is that. So just to give you an example of how this goes, this is kind of a summarized kind of dialogue that happened kind of in a similar way between different members of the committee when we were talking about just one particular aspect of whether to add this little feature X to contract assertions. And so, one person says, well, X is unacceptable, that's just wrong. And the other person says, no, it's great, we actually tried it out. We can do Y and Z with X, so X is great, and also it's safer. And then Alice says, but it's still wrong. And also, I don't agree with the definition of safer, so that's the other problem we already discussed. And then Bob says, but we've tried it, and we saw it works in our code base. And Alice says, but your code base isn't representative. Like other people have different code bases that have different properties. And also, it's just not good language design. And Bob says, well, it doesn't matter whether it's good language design, it matters that it works. And then Alice says, but it's too complicated. I don't know how to teach this. And then Bob says, but teachability is not about simplicity. It's about how easy it is to use contracts. But X doesn't make it easy to use contracts. Yes, it does. And so it goes on and on and on and on. And then, here's a bunch of examples where design X just completely falls apart. I don't agree. All of these examples, they're already broken before you even add contract assertions. But X doesn't work if my code isn't const correct. So if I just can't put const here because somebody just didn't put const there, then it doesn't work. Then make your code const correct. But I can't, it's legacy code. I can't add the const there. I can't touch this code. Okay, well then if you can't add the const here, add a const cast there. But I can't, const cast is banned by my coding guidelines. People shouldn't be using it. Then change your coding guidelines. Should everyone else miss out on feature X because you have stupid coding guidelines? Really, I don't really think that all the benefits that you claim X has outweigh all the problems you would introduce. And Bob says, well, I disagree. It goes on. Look, here's another thing. X breaks static analysis. No, it doesn't. Yes, it does. I'm an expert in static analysis. No, it doesn't. I'm an expert in static analysis too. So this is the reason that standardizing contracts took 21 years. So basically, I needed to figure out how to deal with this. And it turned out to be hard, but I learned a few things. And I want to share them because maybe it's useful for a few people who have similar problems. So I kind of figured it out the hard way, but let's give you a little bit of context. So W21, aka the C++ committee. Now, if you have a bunch of subgroups, each proposal has to go through all of them and be approved by everyone. The composition of the people in these groups is unfortunately very far away from being demographically representative. Mostly, it consists of very senior C++ experts, which tend to have been there for a while, or at least some of them tend to have very strong opinions, a very particular communication style. Some are sent by tech companies who have a very vested interest to do X or not do X. And others, they don't really care. They're busy with other stuff. They don't really listen to whatever is going on, but they still vote on stuff, right? And then most people don't actually read the papers. That is unfortunately one reality. So, and the other thing is that decisions are made by consensus, which means that a big majority of people in a room needs to agree on this is the thing you want to do. And if there's no consensus, nothing happens. And we know this from other things like why we still have daylight saving time in Europe, because the European Parliament already agreed, I think in 2019, that we want to get rid of that, but now the countries can't agree on whether we want to keep summertime or wintertime. Right? If there's no consensus, nothing happens. So how do you make stuff happen? And this is kind of the really hard problem that I needed to figure out how to move past. And so the number one thing is this. I learned this the hard way. You need to have patience. And so I call this the art of cat herding. And there's some general rules that I just, maybe you're going to read this in every book on this topic, but I kind of had to figure it out the hard way. But these are some rules that I figured out you should never violate, right? You should always be respectful and professional. Never assume bad intent, and always have a transparent process and apply it fairly when you deal with everybody. You have to be prepared to explain the same things over and over and over and over again because people don't read papers. And if someone disagrees with the group, make them articulate what they want instead. Oh, you don't like X? What do you want us to do instead? Like, can you explain that? Can you write it down? And if they say, okay, I can write it down, then they're committed. Then a week later, you can tell them, did you write it down already? Did you write it down already? Politely, but. And then if multiple people in the group have a disagreement and everybody's kind of watching and they don't know who's right, tell those people, okay, you and you have this disagreement about this thing, go off and figure it out, and then come back when you agree. And then they say yes, and then, again, a week later, you can say, have you done that yet? Can I help you set up a meeting? Can I maybe moderate the meeting if otherwise, you can't figure it out? And facilitate that process. So I found that to be very helpful. Follow up. And then there's a few rules about the technical discourse. So one thing that I found is really, really important, as I think hopefully is evident from this little dialogue I showed earlier, is that I found that it's really helpful to always focus on facts, data, and things that you can objectively verify, right? And avoid things that are biased or contain a value judgment. So for example, if somebody says, A is better than B, that's not helpful, Make them reframe it as X prioritizes A instead of B, Y prioritizes B instead of A. Is A or B more important to prioritize, right? That doesn't contain a value judgment. It doesn't say something is bad or better or worse. It just says, do you want to prioritize A or B? And why? Can you justify that decision, right? And don't be afraid to challenge other people when they fail to do this, right? So if somebody says X is just wrong, don't be afraid to say this. Right. Learn to distinguish facts from opinions. We had, for example, people simultaneously claiming that contexts are too large and claiming that contexts are not large enough. So both of those statements can't be true simultaneously. So challenge that, right? If somebody says, this feature is too large and too complex, ask, which part can we remove, without compromising adoption of the feature. If somebody says, they're not large enough, they're missing feature X, okay, but maybe we can add feature X incrementally in the next release. Maybe we don't have to agree on this now. Learn to distinguish facts from non-facts. People have said, as I heard most recently actually somewhere on a certain social media platform that I don't want to name, contracts are not baked yet. Well, I think it's the most well-considered and well-researched feature we have ever standardized. You can disagree on that. That's your opinion, but there's some facts, right? This is a hard one. Learn to recognize logical fallacies. Here's a few examples. Somebody says the purpose of contracts is to do X. For example, remove undefined behavior from the language. And then contracts are not actually doing X. So contracts are bad. Of course, the fallacy is that contracts were never designed to do X. There's another thing that's designed to do X, which is complementary. Another fallacy is contracts suffer from problem Y. Therefore, we should not standardize contracts until we solve problem Y. This is, again, a fallacy if problem Y actually has nothing to do with contracts. I have an example for this. People are saying, we need to figure out the ABI story. Yes, that is a big problem. If you have a translation unit with checks off and another translation unit with checks on, and you compile them together and link them together, you need to think about ODR, and you need to think about, what's the ABI? Is there a way to make the ABI understand what's going on? Can I reason about whether the checks are going to be, on or off in the resulting program? But it turns out this problem actually has nothing to do with contracts. This problem is a consequence of how linkers work today, how the ABI works today, right? So any design that has, anything like a runtime check that you can turn on or off, however you design it, is always going to run into this problem, right? And it turns out that, there's three things you want to solve this problem. You want backwards compatibility. You want deterministic behavior. You want to reason about whether the checks are on or off. And you want no runtime overhead. And it turns out you can just only get 2 out of these 3, right? That's just a fundamental property of how C++ works. And there's nothing we can do to design our way around it. You just have to choose which 2 out of these 3 you want. And then depending on that, your compiler is going to, do this ABI or that ABI or apply this or that strategy. It has nothing to do with the design of the feature. Another example is, this design is wrong because it doesn't follow the principles of Bertrand Meyer's design by contract. Now, Bertrand Meyer invented design by contract in the 80s and implemented a programming language called Eiffel, which was based around that. And at the time, it was a big achievement, right? Big step towards all of this stuff. But that was in the 80s. And today, we know, for example, that this model is not applicable to C++ because C++ is a very different programming model from Eiffel. And we also know that actually this model is both incomplete and incorrect. We know that today. We didn't know that 40 years ago. I'm going to write a blog post about that, a deep topic that's going to be its own talk. So, and if there's at the end of this a disagreement between, do you want to do A or B? And you have to argue, for A or for B, you already lost. That never works. If you're at the stage where you have to convince somebody that they're wrong and you're right, it doesn't work, in my experience. That's just how human psychology works. So don't try to do that. Instead, help people see the correct solution for themselves. This is how you convince people. And the other thing that I learned that's really interesting about this is that one very good way of doing this is to visualize it, because people work very well with visual input. Right? And so I actually figured out a way to do this, kind of an algorithm. Whenever, last year, we had a big design disagreement, I just applied this algorithm again and again and again. It helped us go past big disagreements. And I'm going to keep applying it in the future. And hopefully it's going to be successful. And hopefully it's going to be helpful for other people too. So in the last 5 minutes, I want to quickly talk you through how it works. So I didn't invent this from scratch. This is all based on a framework actually designed by John Lakos, who's here in the room. So there's a paper about this, P3004, called Principal Design for WG21, which was an attempt at kind of proposing an algorithm for how to make these decisions for the committee. Turns out it doesn't quite work. It's a great idea, and you can apply it for all kinds of things. Like, for example, me and my wife used this algorithm to decide where we're going to go on summer vacation this year. It worked brilliant. But on the committee, it didn't quite work because it's quite complex. It has lots of moving parts, lots of places where you have to do very fine-grained things, and the committee as a whole doesn't have the time, doesn't have the patience for that. So I had to simplify it a lot. And so the result is this much simplified version of this, which I actually, and also somehow modified in a few places, that I found to be actually effective when you're dealing with a group of people like this. So here's my method. First, state the problem. For example, this is one design decision that we had to make. Should pre and post be allowed on functions that are defaulted on their first declaration? Yes or no? So state the problem. This is what we're trying to figure out. Then list the requirements, right? We don't want runtime overhead when you put pre and post on those things, and we don't actually check things. We don't want to silently like omit or allow omitting checks that the user said they want to be checked. We don't want to change whether the function is trivial or not, because that allows you to branch on whether you enabled or added a contract assertion. That's a bad thing, etc., etc. So just list them all. Anybody who's a stakeholder and just gets to list their requirements. Now, this is the difference between my version and John Lagos's version. Do not rank them into more or less important. So if you can do that, great. But typically, when you're dealing with people who have very different opinions, they will never agree on which requirements are more or less important, because they have very, very different priorities. They come from different industries, different companies, different use cases. They will not agree on those things. You're going to lose a lot of time trying to make them agree. It's not going to go anywhere. So all requirements are created equal. And there's some forbidden words: good, bad, important, crucial, fundamental principle. Anything like this that contains a value judgment or a bias, can't use that. You have to objectively state the requirement, and they need to be objectively verifiable. So you need to be able to objectively verify whether a solution actually satisfies it. So you can't include things that you cannot measure, like complexity or teachability, unless you actually can measure it somehow. You have data on this, but typically you don't. You don't include things that you don't have data on, like somebody claims this is a common use case. Do you have data? Yes, great. If not, you're not going to include it. And don't include requirements that are impossible to satisfy. Like, for example, we want wide deployment in the field of a feature that we haven't even standardized yet. That's probably not going to happen. So you list the requirements. Then you list all the proposed solutions, right? So that requires you to understand them all and write them all out. And then you make an evolution graph, like which solutions can be evolved from other more conservative solutions. So for example, solution A is a very conservative approach, makes everything ill-formed, but you can evolve it into B or C. But you cannot evolve B into C. You have to choose between B or C. And now you construct a table where every solution is a column and every requirement is a row. And then in each cell you put whether the solution satisfies the requirement. And in the original method, this very fine-grained, you can put lots of numbers in there. In my version, there's only 3 possible values: yes, no, maybe, partially, under certain conditions. And you make that green, red, and yellow. So it's very obvious, very nicely visualized. And so it looks like this. And so here you see C is obviously the right solution, and everybody agrees. Or maybe C has a little trade-off here, and then you can discuss, are we okay with this trade-off? Or maybe it's like this, and then you can only satisfy requirement 3 or 4, but not both. And then you need to actually talk about which requirement is more important. But you're going to only talk about this one thing, right? Everything else you already agreed on. This is the only decision you need to make. This is the only thing you need to get people on the same page on. That makes everything a lot more effective. So you discuss conflicting requirements, you agree on the right trade-off. And if you can, great. If not, you fall back to the next conservative thing in the graph. And that's it. So I have an example. Can I just have 1 more minute to show the example, Phil? I guess yes. OK. So the example is, how should contact assert interact with no except? And if you write something like no except x, contact assert x, should that be true or false? And we had bitter disagreements about this. So this is what the matrix looks like. So we got 5 different solutions, 4 different requirements. We got like a few things where this has like an annoying trade-off, this has an annoying trade-off. What should we do? And here's a case where we really have to like choose one requirement that we can only satisfy 3 out of 4 things. Like, which 3 do we want to satisfy? But something interesting happens sometimes when you do this, because it's so nicely visualized. People can easily work with this. So when we were looking at this, Lisa Lippincott, who joined the teleconference where we were discussing this, she just looked at this and she said, oh, wait, hang on a minute. You overlooked a solution. There's a solution I can think of that satisfies all 4 of those things. And that's a solution that we have in C++26 now. Just make it not an expression, but a statement. Right? So this is the algorithm. I've seen it work. I applied it successfully on a group of very, very stubborn and opinionated engineers, and we managed to agree on stuff. And so maybe this is going to be useful for somebody else as well. I am planning to apply this more as we add more stuff to contracts. Like, we still need to agree on how pre and post and virtual functions should work. This is going to be a big thing for C++29, and lots of other things, and hopefully also, for other features in other areas, and maybe even outside of the committee. Right, so that is contract safety and the art of cat herding. Thank you very much.